personal congratulations to you all on achieving your awards today from Liverpool John University, LJMU, in association with YPC. Everyone is very proud of your achievements and are delighted with your success.
Exciting, it's very exciting.
Saya rasa gembira dengan kejayaan anak saya berjaya menamatkan pengajian di YPC dan hari ini adalah hari yang paling gembira lah pada saya kerana di atas kejayaan.
Actually very excited, super excited actually.
Kind of feeling happy, very happy.
It's a good
Personal congratulations to you all on achieving your awards today from Liverpool John University, LJMU, in association with YPC. Everyone is very proud of your achievements and are delighted with your success.
exciting, it's very exciting.
Saya rasa gembira dengan kejayaan anak saya berjaya menamatkan pengajian di YPC dan hari ini adalah hari yang paling gembira lah pada saya kerana di atas kejayaan.
Actually very excited, super excited actually.
Kind of feeling happy, very happy.
It's a great honor that I can graduate with Liverpool John University degree.
I can invest my career in multiple spectrum. I am more versatile for all the challenges that I have to face.
After graduation, I'm going to continue working and explore the world with my current company. Other than going to Japan, we're also looking forward to expand the team to Singapore and as well as other countries in Asia.
Liverpool John Moore University itself, a 200-year-old university that is really world-class and world-ranking. And what does it do to you? It opens the door to future job employability, not only in Malaysia but also all over the world.
YPC International College is a very well-respected partner at Liverpool John Moores University. We're very glad to see another big cohort of students graduating today. Congratulations.
Assalamualaikum dan selamat sejahtera kepada pegawai-pegawai PPD, semua pelajar, guru-guru dan ibu bapa yang menghadiri seminar Jom Skor STPM 2024 semester 2 bagi mata pelajaran fizik bersama Cikgu Jaya Salvi. Program ini merupakan program jaringan kolaboratif strategik YPC International College bersama Victoria Institution. Anda bersama dengan saya, Cik Diba, selaku pengerusi majlis pada hari ini. Bagi pelajar yang sedang online, kalau boleh dengar suara saya dengan jelas, minta tolong respon di ruangan chat box. Bersama-sama dengan kita pada hari ini adalah Yang Berusaha Abdul Samad bin Othman, Pengetua Victoria Institution, Puan Salinas binti Saad, Guru Penolong Kanan Takbir dan Kurikulum Victoria Institution, Puan Zufrizah Ariyati binti Muhammad Fazim, Guru Penolong Kanan Tingkatan 6 Victoria Institution, serta guru-guru dari Victoria Institution, Cikgu Jaya Salvi, Guru Mata Pelajaran Fizik, Datuk Dr. Noel Robert, Pengetua YPC International College, Dr. Farah Robert, Pengarah Urusan YPC International College, Kaunselor Akademik YPC. Seterusnya, tetamu jemputan kita pada hari ini iaitu pelajar-pelajar STPM dari seluruh Malaysia. Terima kasih juga kepada ibu bapa dan guru-guru yang turut hadir pada malam ini. Sebelum memulakan agenda utama kita, suka untuk saya ingatkan beberapa perkara terlebih dahulu. Pastikan mikrofon anda dalam mood senyap. Pinkan nama wakil yang akan berbicara sebentar lagi untuk melihat slide pembentangan. Pastikan anda bersedia bersama buku catatan untuk mencatat isi-isi penting. Sebarang pertanyaan, boleh terus bertanya di ruangan chat semasa sesi Q&A. Diingatkan kepada semua pelajar untuk tunggu sebentar setelah kelas tamat bagi mengisi kehadiran untuk tujuan sijil penyertaan. Sebelum itu, semua pelajar dan guru-guru dijemput untuk follow dan subscribe media sosial YPC International College di laman sosial Instagram, Facebook, TikTok dan YouTube kami untuk mendapatkan info-info program dan seminar yang akan datang. Sebelum memulakan program kita pada hari ini, saya ingin menjemput Puan Zulfrizah Aryati binti Muhammad Fazim, Guru Penolong Kanan Tingkatan 6 Victoria Institution untuk memberikan sepatah dua kata. Dengan segala hormatnya, dipersilakan.
Okay, terima kasih saudari pengerusi majlis, Cik Diba. Pada masa yang sama, beliau juga merupakan pegawai liaison kita di Victoria Institution berkenaan urusan-urusan kolaborasi bersama dengan YPC International College. Saya ingin mengambil peluang ini untuk mengucapkan ribuan terima kasih kepada yang berusaha, Pengetua YPC International College, Datuk Dr. Noel Roberts atas peluang yang telah diberikan kepada kami untuk bersama-sama terlibat dengan segala aktiviti program yang dapat membantu meningkatkan prestasi murid-murid Form 6 untuk STPM tahun 2024. Kami berasa cukup bersyukur dengan segala yang telah dirancang dan akan dilaksanakan bersama dengan YPC, dan kita juga rasa bertuah pada malam ini Guru Cemerlang PTE Victoria Institution iaitu Puan Jaya Selvi sudi untuk berkongsi pengalaman bersama anak-anak murid PTEVI dan anak-anak murid seluruh Malaysia yang mengambil subjek fizik. Saya memesan kepada semua student agar memberi perhatian sepenuhnya kerana tip-tip yang Puan Jaya Selvi beri nanti sangat berguna untuk anda menghadapi peperiksaan fizik pada minggu depan. Now, aside from that, I would like to also remind all of you, when you are preparing for the exam, there will be a time where you need to stop studying, but you have to start relaxing and calming yourselves down so that you are at peace when you enter the exam hall. Okay, you cannot be taking the exam feeling nervous. Okay, you've done all the studying you can do. You've gotten all the tips and all the guidance from teachers. You are ready. You are prepared. So all you have to do is answer the questions. All right. That's all from me this evening. I wish you all the best and have a good session with Puan Jaya Selvi. Thank you, Ms. Diba.
Terima kasih Puan Zulfrizah atas ucapan sebentar tadi. Seterusnya, saya ingin menjemput Miss Azmira, pensyarah daripada YPC International College. Dengan segala hormatnya, dipersilakan.
Okey, boleh dengar suara saya ya? Okay, terima kasih Puan Zulfrizah, Guru Penolong Kanan Tingkatan 6 Victoria Institution di atas perasmian hari ini seminar SKOI STPM. Terima kasih Cik Diba juga MC pada hari ini. Assalamualaikum dan selamat sejahtera. Saya Miss Azmira adalah salah seorang pensyarah akademik dan juga penyelaras program untuk program pengurusan perniagaan di YPC College ini ya. Alhamdulillah kita boleh tengok kat sini kita dapat bersama-sama dalam Zoom hari ini ada kawan-kawan maybe daripada pelbagai tempat yang berlainan, tapi kita boleh duduk dekat sini sama-sama dapat gunakan platform online, platform virtual ini untuk kita buat kelas tambahan diadakan secara percuma. Terima kasih kepada Datuk Noel dan juga guru-guru yang committed dalam terlibat dalam usaha ini. Untuk pengetahuan semua yang tak tahu mengenai College YPC ini, kami YPC terletak di Padang Perdana. Di mana kita dekat sini di YPC kita ada tawarkan program daripada level certificate, foundation, diploma dan juga degree level. Apa yang menariknya dan berbezanya college kita dengan college lain, di mana kita di YPC kita tawarkan UK degree dan dalam masa yang sama our objective, our vision adalah untuk membantu golongan-golongan B40 dengan affordable price, harga yang mampu milik, di mana adik-adik hanya belajar di Malaysia sahaja, tak perlu pergi ke luar negara, tetapi sijil degree adik-adik dapat pengiktirafan daripada UK. Ini adalah kerana kita berkolaborasi atau partner institution kita adalah LJMU. LJMU adalah Liverpool Johmore University, di mana universiti ini adalah World Ranking University. Untuk adik-adik pada malam ini adalah laluan adik-adik selepas STPM adalah menjadi lebih singkat. Lepas STPM boleh terus apply degree dengan cepat hanya 2 tahun. Dan bila adik-adik dapat UK degree ini, kalau ramai yang tak tahu, sebenarnya diiktiraf di mana-mana negara yang adik pergi. Boleh bekerja di Malaysia, Singapura, UK, Dubai dan mana-mana negara kerana this is world ranking university dan sangat senang mendapat peluang pekerjaan. So, salah satu program yang kita tawarkan adalah business management, di mana Miss sendiri adalah program coordinator penyelaras program, dan kita juga ada program lain yang juga partner dengan LJMU, di mana kita ada program accounting, IT, komputer, di mana program-program ini adalah program yang mendapat permintaan yang tinggi, demand dalam dunia pekerjaan lah. Untuk adik-adik lebih lanjut, adik-adik boleh terus pergi website kita. Dekat situ dalam poster kita ada cakap YPC scholarship kita offer, based on interview session dan result adik-adik lah. Untuk Miss kongsikan sedikit untuk program business management. Ini adalah salah satu program yang paling praktikal dan Miss percaya ini adalah program yang paling senang terjamin untuk mendapat peluang pekerjaan. Macam adik-adik semua tahu, di mana-mana industri yang you all pergi, memerlukan individu pekerja yang ada skill untuk membantu dalam industri perniagaan. So dalam satu program sahaja, dalam satu program business management, adik-adik dapat belajar dan teroka bidang-bidang lain seperti marketing, finance, IT, economic, human resource dan banyak lagi. Ini adalah silibus-silibus yang kita cover dalam program kita lah, dan semua ini sangat mendapat trend dalam pasaran. So boleh share next slide, di mana Miss nak kongsikan alumni kita yang berjaya, because kita cakap melalui pengalaman graduan kita yang berjaya mendapat tempat di MNC company dan well-known company dalam satu program business management. Tetapi daripada sini adik-adik boleh tengok mereka bekerja di dalam industri yang berbeza dan juga di dalam bidang yang berbeza. Dalam program business management kita ada alumni kita Alif Abdul Razak dan sekarang masih bekerja senior HR advisor in Shell. Dan silibus kita memang kita akan ajar berkaitan dengan human resource ataupun people management, and then kita juga ada alumni yang bekerja dalam bidang finance walaupun mengambil program business management, dan ramai sebenarnya juga alumni kita yang bekerja dalam bidang banking. And then juga of course marketing, department, operation, project management, digital analysis dan juga entrepreneur itself lah. So Miss berkongsikan berkenaan dengan business management, tetapi juga di YPC kita ada juga program-program lain yang ditawarkan. Miss rasa pada malam ini itu sahaja perkongsian untuk YPC kita, and then Miss jemput cikgu pada hari ini, Cikgu Jaya Salvi, yang merupakan Cikgu Cemerlang seperti apa yang dikatakan oleh penolong kanan tadi. Beliau sudah berpengalaman mengajar selama 28 tahun dalam STPM ini. So Miss jemput Cikgu Jaya Salvi. Terima kasih.
Thank you, Miss Azmira.
Welcome.
Yeah. Hi, everyone. Hope you're all doing great. Thanks for attending today's seminar. I hope that today's session you'll be able to benefit and clear all your doubts on certain sections that I'll be covering. Our exams are in the next week, Wednesday, the STPM physics paper. So I hope you all are all well prepared. Good luck. So we can begin now. I shall share my screen. PowerPoint. Is it clear, Miss Azmira? Can you see? Okay, can it be, can the screen be seen? I shall now go to slideshow.
Yes, Cikgu, I can see it.
Okay, okay, thank you, Ms. Deepa. Yes, so today I will look at sample questions and answers, okay, and right technique to answer these questions. I will just touch on certain topics that are quite challenging. Okay. Now, if we look at a typical STPM question, there are the qualitative, quantitative, graphical parts, isn't it? So, so I will be covering these sections, okay? Oh, why? I think I can't see my slide. Oh, okay, okay, capacitor. Okay, so we'll start with capacitors first, okay? I just try to clear this section first. Okay. Okay, so in capacitors, sometimes there are questions which ask you to suggest ways to increase the capacitance of a capacitor. Now, we will have to refer to the equation, right? Okay, so what is the equation that relates to the capacitance of a capacitor? Yes, we know that, hold on, I'm just checking my pointer. Okay, so we know that the capacitance is equal to epsilon R, epsilon naught A over D, right? Epsilon R, epsilon naught A over D. So if we were to increase the capacitance of a capacitor, we would have to insert a dielectric with a very high relative permittivity. Yes, okay. Then we would also look at the area. Okay, so since C is proportional to area from the equation, we just have to increase the area of the plates. Okay, and we can see that D here is inversely proportional to C. So if we were to decrease the distance between the plates, that would mean we would be able to increase the capacitance. Okay. Okay, now many questions ask us to discuss the changes to capacitance, charge, and the voltage when a dielectric material is inserted, for example, or when the area is increased or decreased, or if the distance between the plates changes. So how do we tackle these type of questions? Okay, first thing, there are two parts to it. The capacitor must be known to whether it is connected to still to the battery or disconnected from the battery. If the question says that the battery remains connected, then what happens to the voltage? Since the battery is connected, the voltage remains constant. Okay. So if you're asked to explain the or discuss the change to the voltage is constant. What about the capacitance? Okay, since the dielectric is inserted, we discussed in the previous slide, the capacitance also increases. Because a dielectric causes the capacitance to increase. And how about the charge? Okay, here we will look at the equation. What equation do we think of? Q is CV, yes. So the charge is proportional to the capacitance when V is kept constant. Okay, so since capacitance increases, charge also increases. Okay, now what if the question is on isolated capacitor, where the battery is disconnected? Okay, so if the capacitor is isolated, hence charge cannot move in or out of the capacitor plates, right? Because it is isolated. So charge becomes constant. The capacitance, of course, we know due to the dielectric, the capacitance has increased. So increases. And what about the voltage? From the equation now, since charge is constant, but capacitance has increased, hence voltage has to decrease because of the relationship that voltage is inversely proportional to capacitance. So voltage decreases. Okay, this often comes out in objective questions. Okay, let's look at another capacitor question, which is to calculate the net capacitance. Sometimes you have quite complicated circuits. So how would we tackle questions which asks us to calculate the net capacitance? Okay, if capacitors, let's look at the theory. Capacitance in series. Okay, what is the equation we use? We use the parallel equation that we are familiar with in resistors. But this is the formula for capacitance in series. And in parallel, this is the equation. So what if we have a question like this? Okay, example. Okay, sorry. Okay, so if the circuit is like this, now we have to first identify which are the capacitors in series, 4 and 6, right? Because we look at the current to identify. We have current and it splits into I1 and I2. Okay, where the current splits, those capacitors are parallel. If the current is the same, then they are in series. So 4 and 6 are having the same current, they are in series. We use the series equation and simplify for 6 to become 12/5 microfarad. Okay, then this capacitor, the net of 4 and 6 is parallel to 3 because the current is opposite, current is different. So hence, we will use the series equation for capacitors, parallel equation for capacitors, which is simply adding both the capacitance. This is how we tackle net capacitance for a simple circuit like this. Okay, what if the circuit is slightly more complex, like this? So what we do is we simplify from the back, okay, from this part, okay, because the current enters from A and exits through B. So we will simplify from the back, okay. So 2 and 2, since the current is the same, they are in series, so we use the series equation. Then we simplify the diagram so that 2 and 2 is 1, right? Okay, 1. So how does the diagram look like now? We have simplified from a more complex circuit to a slightly simpler circuit. Okay, now we have to identify, I told you all from the back, we move to the front because A is here and B is here. Okay, so 1 and 1, are they in series or parallel? So let's look at the current. Okay, they are different currents, isn't it? Because there is a junction where current can branch. So 1 and 1 are parallel. So we use the parallel equation and simplify 1 and 1 to become 2. Then we redraw the diagram to be to simplify it. So 1, 1 becomes, this becomes 2, and the rest you just redraw them back. Now, how do we solve? So we again look at current flow, okay, because this is a junction, current is going to branch. So current 1 and current 2 here. So current 1 flows through 2 and continues this way because there is no point for it to branch. There's no circuit for it to branch off. Okay, so it continues to current in flowing through 2 continues to the 2 microfarad capacitor below. So that is capacitors in series, which we will calculate, and then we simplify further. Okay, so now we have a more simplified diagram, and we see that both 1 and 1 are parallel because the current branches. So we can find the net capacitance as parallel using the parallel formula where we just add them up. Okay, so from here we conclude that if we have a circuit which is complex, we try to simplify it. Okay, but first thing we have to identify the current. To determine whether it's series or parallel, we check the current. If the current is not the same, they are parallel. If the current is flowing, the flowing is the same, then they are in series. Okay, we continue. Let's look at theory here. That is capacitors. Hold on. Capacitors in series, the charge is constant. Okay. And capacitors in parallel, the voltage is constant. Right. Voltage across all the capacitors in parallel is constant. And for for capacitors in series, the charge is constant. Okay, for example, we see capacitors here. Are they in series or parallel? They are series. So the charge that is stored in capacitor 1, the charge stored in capacitor 2, and the charge stored in capacitor 3 are all equal. Okay, if we look at capacitors here which are in parallel, then we can say that the voltage is constant, right? We are using the second theory, yeah? That the voltage V1, V2, and V3 are the same. Okay, V1 is V2 equals V3. Now let's look at a combination. Okay, so we can say that the charge Q that is stored in capacitor 1 is going to be shared by capacitor 2 and 3. So capacitor 2 and capacitor 3, the charge is comes from capacitor 1. So I can make an equation. Q1 is Q2 plus Q3. Okay. How about voltage? Now the voltage at C1, which is V1, plus the voltage at V2 or V3, because V2 equals V3, right? V2 equals V3. But I can say that V1 plus V2 is the battery voltage, or V1 plus V3 is the battery voltage. Okay. Let's try a question on that. Let's see whether we understand. Okay, here we have an example given. The capacitance is given. The circuit is a combination of series and parallel. Okay, what info else have been given? Let's say that V1, the voltage across capacitor 1 is 10 volt. What would the voltage across capacitor 2 and 3 be? Yes, V2 should be 2 volt because 10 here, voltage 10 here, plus the voltage here must equal the battery voltage. Okay? And since V2 equals V3 because they are both parallel, then V3 is also 2 volts. Okay. Okay, here now we are asked to calculate the charge stored in capacitor 1. So it's very easy because we know the equation is C1 V1, right? Q1 is C1 V1. Do we know C1? Yes, C1 from the info given was 1 micro. And V1 is 10. So we will get 1 micro and 10 is 10 micro coulomb. Okay, similarly, Q2 will also be C2 V2, which is 2 micro. And voltage, which we deduced earlier, is 2. So we have 4 micro coulomb. Whereas Q3 is C3 V3, and C3 from above is 3 micro, and the voltage is 2 from above. We'll get 6 micro coulomb. Let's analyze the values we got. Q1 is 10 micro, whereas Q2 plus Q3, when we add them up, gives us 10 micro. So, like what I earlier told you all, Q1, the charge stored in capacitor 1, will be shared in capacitor 2 and 3 because the charge can divide or branch, isn't it? So 10 micro here is equal to 4 micro and here 6 micro. Okay. Now let's look at energy stored in a capacitor. We're going to analyze energy stored in a capacitor. Okay, what is the form of energy stored in a capacitor? Is it magnetic energy, gravitational energy? It's electric potential energy. Why is it electric potential energy? Because the plates of the capacitor has charge. So when there is charge in the, stored in the plates of the capacitor, there will be an electric field. Okay, there is a voltage between the plates. There is an electric field. Okay, so there is energy stored in the between the plates of the capacitor simply because of the charge. The greater the charge, if the charge increases, the greater the potential energy. If the voltage increases, what do you think? Would the potential energy increase? Yes. It's similar to a battery. If you think of a battery, if we have a battery has a voltage. Compare a battery with voltage 9 volt and a battery 1.5 volt, which has more stored energy, which can light a bulb more brighter. Of course, the 9 volt battery. So when the voltage is higher, the energy stored in the battery is higher. The battery and the capacitor is similar to each other. Both store energy. The only difference is the capacitor's energy. Capacitor discharges very fast, whereas the battery keeps the energy, keeps its charge for a long time. Okay, so if we understand about the battery, we can understand about the capacitor. Huh? Let me clear first. Okay, so let's move on. Okay, if a dielectric is inserted, what happens to the energy of the capacitor? This is a question which is frequently asked. Okay, when changes happen to the capacitor, what also happens to the energy of the capacitor? Okay, but in the condition, the battery is kept connected. We have two conditions. Either the battery is still connected when the dielectric is inserted, or the battery is disconnected. So again, we should understand that if the battery is kept connected, what is constant? The voltage is constant, right? But the capacitance increases, yes, because as we discussed earlier, capacitance increases when a dielectric is inserted from this equation, epsilon R. We insert epsilon R, C increases. Okay, now how do we explain this, that the energy increases? So we must understand that we have to state that more charges flow into the capacitor from the battery, because the battery is still connected to the capacitor and the capacitance increases. So the size is like a bigger pail to store more water. Okay, so the capacitance was smaller earlier. Now the capacitance increases. So more charges are able to store themselves on the plates of the capacitor. Right. Okay, then next. Hence, the electric potential energy increases. And what is the justification that we say that the electric potential energy increases? Because from the equation, energy is half QV. So V is constant, but Q increases, so energy increases. So the main thing is that you have to state that more charges are able to store themselves on the capacitor's plates. Huh? Okay, now let's try a question which involves the battery being disconnected. Okay, here the battery is disconnected, so the capacitor is isolated. Now we know that charges cannot flow into or out of the capacitor. So Q will be constant, but capacitance we know increases. Huh? Capacitance increases because of the dielectric. Yes. No charges can flow into the capacitor. Okay, now what also we have to explain is the dielectric is polarized by the electric field of the capacitor. Because there is an electric field between the capacitor, right, plates, and it causes the dielectric molecules to become polarized. So the molecules, if you look at the dielectric here, I'm drawing that the molecules of the dielectric becomes polarized. On the left is negative, on the right is positive, negative, positive. And what is doing, how is this happening? What is causing the dielectric to become polarized? It is the electric field of the capacitor. If the capacitor plates were empty, there is no charge between the plates. Let's say it's a capacitor that is empty. When you insert a dielectric, nothing happens to the dielectric. But the field now, if the capacitor is charged, then the field is doing work to polarize the dielectric. And this results in the electric field decreasing. The presence of the polarized dielectric decreases the electric field. And when the electric field decreases, the voltage of the capacitor decreases because the equation that relates electric field to voltage is, E is V over D. So when electric field decreases, because the electric field is polarizing the dielectric, the voltage across the capacitor decreases, hence energy stored decreases from this equation. Okay, the same equation we used earlier, that is U is half QV. But in the case for capacitor which is isolated, Q is constant. Okay, but V has decreased, hence the energy decreased. This is opposite to the case when the capacitor was connected to a battery. When the capacitor was connected to the battery, it was opposite. The energy actually increased. Because Q increased, V was constant. So energy increased when the battery was connected. Dielectric inserted but battery connected. The energy increased. But when the battery is disconnected and the dielectric is inserted, the energy decreased. So you must know this difference, because the questions in objective will just ask you to choose the answer correctly. If capacitor isolated, dielectric inserted, energy increase or decrease. So you must be you must know that. Okay, now we are looking at calculation. Let's calculate the energy stored in the capacitor. Okay, what's the formula we use? We discussed it in the previous slide. U is half QV. Energy is equal to charge times the potential difference and divided by 2. So if we have a QV graph, we find that Q is proportional to V for a capacitor, right? So let's draw a capacitor. Let's see, is there a capacitor? Okay, so let's say I have a capacitor here, okay, connected to a battery. Okay, so the battery is going to charge the capacitor, Q is stored. And this is the voltage, which is equal to the voltage across the capacitor 2. The battery voltage is the capacitor voltage. Now, if I increase the voltage, the charge also increases, right? More charge is stored. So that is why we find that the charge increases with the increase in potential. And if we look at the graph, we can relate the energy to the graph. How? By looking at the area below the graph. The area below the graph looks like a triangle, right? It's a triangle. And it follows this equation, half QV. So we can say that the area below the graph represents the energy stored between the capacitor plates, or the energy of the capacitor. Okay, let's try a question. A capacitor is charged by a battery. The battery is disconnected and a dielectric is inserted between the capacitor plates. So you must know that the battery is disconnected, dielectric is inserted, the capacitance will change, the voltage may change, the charge may change. So you have to calculate for that. Huh? Okay, so what else is given? Here the diagram shows a capacitor with the dielectric inserted. Okay, now this is the information given. Okay, that is the initial capacitance, the initial voltage, and the permittivity is given. Okay, so we are asked to calculate the initial energy. What is the equation we use? Now, we can also use half CV square, right? If we were to replace Q as CV, this is the equation we get. And I'm sure you all know that. And we also can use half Q square over C if we replace V as Q over C. So we can choose from either of the three. Yeah? Since the information has capacitance and voltage, I will use the equation half CV squared. Okay? So C is 1 micro and V is 9. So this gives me 4.09 square. Okay. Okay, so can you all calculate what is half CV square? So we have 81 divided 2. We get 40.5 micro joule. Okay. Now, how about U final? For U final, I need to find C final and V final. Okay. So what is C final? C, when the dielectric is inserted, is the dielectric permittivity times the initial capacitance. Okay. When a dielectric is inserted, the capacitance is simply the dielectric permittivity times the capacitance, initial capacitance. So 2 times 1 micro gives us 2 microfarad. So we are going to place C as 2 micro. Now, what about the voltage? The voltage has dropped, isn't it? Because the battery is disconnected, so it's no longer constant. So we can use the fact that the charge is constant. So Q initial is Q final, and try to work out V final. What is Q? Q is CV. C initial, V initial. And Q final is C final, V final. C initial was 1 micro. V initial, you can see above there is 9. C final, we just calculated from above, which is 2 micro. And we are able to calculate the final voltage after the dielectric is inserted. So can you calculate what is 9 divided by 2 is 4.5. So V after the dielectric is inserted is 4.5 volts. Okay, so which I'm going to insert here, 4.5 square. And when you calculate this, I give you some time to calculate. We get 20.25 microjoule. So I will round it, microjoule. Okay, now the next part which is commonly asked is to calculate the energy difference. Now, what's the equation for energy difference? Energy difference is always the final minus initial. Whenever they ask you to calculate difference, it's always final minus initial. So what was the final? 20.3, which we have calculated in part 2, micro, minus initial was 40.5 micro, and we get 20.25 negative. Okay. Why 20.25? Sorry, let me calculate again. 40.5 minus 20.2. It's 20.2, sorry, 20.2 microjoule. Okay. And the answer is negative to indicate that the energy has decreased when the dielectric is inserted between the plates that we discussed earlier, right? So the negative must be placed to show a reduction in the energy. So why did the energy decrease? Recall back. Why did the energy decrease when the dielectric is inserted with the battery disconnected? Because the the capacitor's electric field, okay, polarized the dielectric. Work was done by the capacitor to polarize, and this caused the energy to drop, because the voltage dropped. And when the voltage of the capacitor dropped, naturally it has less energy stored. Just like a battery, as I told you all, if the battery has a lower voltage, you are not going to let it light up a bright bulb, isn't it? You would take a bulb with a higher voltage to light up your bulb. Okay, so what shall we do? Now we have finished capacitors, the sections that I wanted to discuss. I thought of moving on to electromagnetic induction because this is quite challenging or more difficult topic. Okay. Okay. Now, when we think of electromagnetic induction, we have to remember Faraday's law. So everything rests on this law that the EMF induced is negative the rate of change in magnetic flux linkage. Okay. And what is flux? Flux is, if we look at the equation, NBA cos theta. Okay, so this is the equation that you will commonly use in this topic. Okay. Okay, so let's understand more about electromagnetic induction with this simple question. Can you read the question? Okay, a rectangular coil moves at constant speed through a uniform magnetic field as shown in the diagram. Yes, so the coil enters the field, okay, and exits the field. Oops. Okay. Okay. Draw a magnetic flux against time graph as the coil enters and leaves the field. It's a bit challenging. So you see, you have a question like this. How do you draw the flux time graph? First thing, you have to draw the axis, okay? Now, we also know that flux is NBA, right? N doesn't change. B is the magnetic flux, doesn't change. But we find that as the coil enters the field, okay, we find that the area that intercepts the magnetic field increases. So we can say that the flux increases, okay, because the area that is coming into the magnetic field is increasing. Then as the coil moves in the magnetic field, there is no change to the area. It's a fixed area. The coil keeps on moving, but the area that is intercepting the field doesn't decrease or increase. So the flux remains constant. Now, when the coil exits the region, the magnetic field, the area that is intercepting the field is decreasing. Okay, less and less of the area magnetic field is passing through the coil's area, so the flux decreases. So this is the graph, the complete graph, where you have labeled the magnetic flux, time, and you've drawn the correct graph. Okay, what if the question follows up with this? Draw a corresponding induced EMF time graph. So how do we do this? Always go back to the equation. What is the equation that relates EMF and flux? EMF is equal to the rate of change in flux. Can we see the rate of change of flux in the graph? Yes, it's the gradient of the graph, right? So this is d phi dt, right? The gradient. Here no gradient. Here there is a gradient. So that is what you're going to plot. So first thing, draw the axis. E against time, then section by section. Okay, here you see an obvious increase in flux. So the gradient is also positive. D phi dt is positive on the left hand side here, on this side. Okay, so but don't forget there is a negative here. So negative of a positive gradient gives us negative. So can you see that the EMF is constant because the gradient is constant. For this time period t, from 0 to t, the gradient is constant. So the flux is constant. Then in the second part, from T1 to T2, the gradient doesn't change. So the EMF induced is 0 because there's no change in EMF. And for the third section, because the gradient is negative, so negative of negative gives us positive. So this is how the EMF graph is drawn. So we can see that when the flux increases, the EMF induced is negative. And when the flux decreases, the EMF induced is positive. This is based on what? Lenz's law. Because EMF is induced to oppose the change. So when there is an increase in flux, the EMF direction is to create a magnetic field to oppose. So the direction of EMF is negative when flux increases and the reverse. I hope you all understand this part, that it is important to consider the negative and positive sign and understand for why the EMF is positive and negative. Let's try with a simple example. Okay, here it's like a calculation question, but relating to the graph also. Let's say the initial flux is 0. There you can see here the initial flux is 0. And let's say the final flux is 50 Weber. If a question is given that the initial flux is 0, final flux is 50, and the time taken for this change is 2 seconds. How do we calculate the EMF induced? So we go back to the equation. When we put in the values, negative, final, it's always final minus initial over the time taken, and we get negative 25 volts. So you can see the negative is appearing here when the flux is increasing. And the value, if you look at the graph, this value is 25 volts. And if we were to change the values where initial is 50 and final is 0, then we would get negative 0 minus 50 because final minus initial. And that would give us a positive value. So when the flux decreases, the EMF would become positive. Okay, let's look at the qualitative question which needs explanation. This is a question where let me see, is it similar? No. Yeah, something similar, a coil. but slightly different. Let's look at the diagram. A coil is brought into a perpendicular magnetic field by a force. It is observed the coil moves into the magnetic field, sorry, not into the coil. The coil moves into the magnetic field with constant speed, like this. So we have a coil moving into the magnetic field. This is the coil moving into the magnetic field, and it's observed that the coil moves with constant speed. Explain why the coil moves with constant speed when a force is applied. Because when we apply a Newton's law, whenever a force is applied, okay, and there is no mention of retarding force, that means this is the net force. So if we were to use F is ma from Newton's law, second law, we would assume that the coil would accelerate. Okay, but here it's stated that the coil is moving with constant speed when the force is applied. So you are supposed to explain why that happens. Okay, this has come out in objective questions. I'm not sure if it will come out in the structure or essay. It has in the old papers, I mean, before 2013 it has come. But so far, in the latest papers, it has not come out yet. Okay. So to understand in your objective questions, let's look at how the theory, how it works. Okay, so first thing is magnetic flux in the coil will change, right? The coil is moving into the magnetic field, and here the magnetic field increase. The magnetic field, the flux through the coil increases, and based on Faraday's law, EMF is induced. Now, use Fleming's right-hand rule to determine the direction of EMF. Okay. When you use Fleming's right-hand rule to determine the direction of EMF, we get the EMF to be, because this is the section of the rod that is going into and cutting the magnetic field. So the EMF direction is this way. So this is negative, positive. Hence, the current that flows is in the anti-clockwise. So there is an induced current flowing in the anti-clockwise direction, and this is based on Lenz's law. But look at the points. You just have to mention magnetic flux is increasing, EMF is induced in the coil. This is based on Faraday's law. Induced current flows in the coil based on Lenz's law. The explanation using Fleming's rule is not required. Now what happens next? If there is current flowing in a coil, in a conductor, that is in the presence of a magnetic field, what theory are we using? We are using the theory in magnetism that magnetic force will act on a conductor of length L carrying current I placed in a magnetic field. So there is a magnetic force. And when we use Fleming's left-hand rule, we find that this force is, let me change the pen color to blue. We find that this force direction is this way. The magnetic force is in the opposite direction to the applied force. The applied force is bringing the coil into the magnetic field, but a magnetic force is in the reverse direction. Now it makes sense why the coil moves with constant speed, because the magnetic force is equal to the applied force, but equal and opposite direction. So this makes the net force become 0, okay, and hence the velocity is constant. So you must be able to know where is the direction of the magnetic force. Always remember it's opposite to the applied force. And the flow of explanation is like this. Whenever you mention EMF is induced in an explanation question, you must mention this is based on Faraday's law. This is the justification that gives you a point. You can't just state, oh, EMF induced. Next point, current is induced. You have to mention that it's based on Lenz's law. The direction is based on Faraday's law, for example, and so on. Okay, let's continue with the next part. Here we are looking at derivation now. So in this topic on electromagnetic induction, we have looked at the qualitative part, which is explanation. Okay, now we are looking at derivation. Okay, we are looking at derivation of the earlier problem. Okay, what are we asked to derive? Derive the induced EMF in the coil. So do you recall earlier when we discussed the coil enters the magnetic field, there is an EMF induced in the coil, okay, which creates the current, and a force acts in the opposite direction. So we are asked to derive the EMF. It's very easy. All you need to do is recall back Faraday's law. So EMF is equal to the rate of change in flux. So straight away we write this, as I told you all, electromagnetic induction hinges on this equation. Now we just inserting the value of flux. Sorry, not value, but the expression for flux. What is the expression for flux? In full, it is NBA cos theta, right? But we need to modify according to the equation. And here, N is 1 because it is mentioned that it is a single loop, NBA. So N is 1, cos theta is 1 because theta is 0. The normal to the area and the magnetic flux is parallel. You can check later. So the angle is 0, hence cos of 0 is 1. Okay, now we are going to insert that here. So this is how you will derive every time. Okay, but I took out the constant. Now, between B and A, which is changing? The area. As the coil enters the field, the area through the coil is changing. So we take out B and leave the rate of change in area. Now, what is the area of the coil? They have given the term W and L for the sides of the coil. So we're going to replace area as WL. Every insertion gives you marks. So this is also giving you marks. This is giving you marks. Faraday's law is giving you marks. Okay. Now, once we've inserted area is WL, we need to check between W and L, which is changing as the coil enters the magnetic field. Now, L is changing because the length that is passing through the coil is increasing. As the coil enters, there's more and more of the length coming into the coil, into the field, but the width does not change. The width remains. Okay, so we will differentiate L towards time. And what is the rate of change of length? The speed. Okay, dl dt is v. So I think we have completed it. There's nothing else to derive because we have derived the induced EMF in terms of the values given in the question B, W, B. Okay, you can't leave it as area. Okay, because area is not mentioned in the text, in the question, right? Okay, let me clear first. Now, what if the question followed up with derive the induced current that flows in the coil? Since we've already calculated the induced EMF, induced current we use Ohm's law. Because a coil is a conductor and the resistance has been given. So by using Ohm's law, we can replace EMF as IR, okay? And with that, we are able to easily derive the current. Okay, so sometimes when you see a question that is on electromagnetic induction, that is on derivation part, it may appear complex, but start with Faraday's law, then insert the relevant flux, and you find that the rest is just following through. Okay. Okay, now we will go to the next part, the last part of electromagnetic induction, which is mutual induction. Okay. Explaining the phenomenon of mutual induction is very popular. Mutual induction, self-induction. Okay, so I'll touch on mutual induction because it rarely comes out, but it has come out recently. Okay, so it may come out again, but I want you all to also look at self-induction together. Now, this is a qualitative question. To explain the phenomenon of mutual induction would easily be 5 marks. So first thing you must understand is that you will need a primary coil and a secondary coil. Here the example given I have put up is a transformer. A transformer uses the phenomenon of mutual induction. Okay, so I'm going to explain based on the transformer. It's best that you draw a circuit, okay, to explain your points. You can draw coils or you can draw the solenoid, okay. Now, what is happening? You must have an alternating current in the primary coil or a changing current. So as long as there is a source that is causing the current to change, current in the primary coil changes, must change for an EMF to be induced. Okay. Next is when the current in the primary coil changes, you can see the blue lines there. Those are the magnetic field created by the current. Now, what is happening if the current in the primary coil changes? What is happening to the magnetic field? The magnetic flux linkage in the primary coil is also changing. And we see that these blue lines run into the secondary coil, right? Through the iron core. So that must be explained, that the magnetic flux is also felt in the secondary coil. The change of magnetic flux is linked and sensed by the secondary coil. This point is very important. Sometimes students miss out on this point, the linking between the primary and the secondary. Okay. Now what happens? If the magnetic flux linked in the secondary coil is changing, now we look at Faraday's law. What is Faraday's law stating? That an EMF is induced. Okay, in where? In the secondary coil, and this was based on Faraday's law. So these are the points to explain the phenomenon of mutual induction. The mention of primary coil, secondary coil, current changing, magnetic flux changing, the link with the secondary coil, and hence finally EMF is induced. Okay. Okay, here is the equation that we use when we are looking at mutual induction. So this is the EMF induced in the secondary coil is the mutual induction between the two coils times the rate of change of current in the primary coil. This is one of the formulas that you would have memorized when it comes to mutual induction. So this is our Vs, Vs here, and this is the current that is changing in the primary coil. Now there's another formula that you have learned in Form 5, Form 4, Form 5. Okay, sometimes we don't learn that in Form 6, but you need to know, because sometimes, let's say if the number of turns in the secondary and primary coil is given, and the primary voltage current is given, then we can easily find the secondary voltage current without having to use this. If let's say M was not given, but N was given, Okay. Okay. Now we are going to look at analyzing mutual induction using Lenz's law. We are analyzing Lenz's law in mutual induction. Okay, what type of questions would be asked? Okay, let's say we have two coils. Here is again mutual induction. Mutual induction is when you have two coils and one coil becomes the primary because there is a source, a voltage source, and the second coil is sensing the change in magnetic field and EMF is induced. So the meter there in coil A is to show the EMF induced or the current that flows, the induced current. So this magnetic field or the blue lines is generated by the primary coil, B. Okay, let's follow up with the current direction. Let's look at the primary coil and see the current direction. Current is flowing like this, right? Oh, sorry, it's not correct. The current direction here is not correct. Because the magnetic, let's forget about this and look at the magnetic field. The magnetic field is running this way. That means this side is north and this side is south. So we will use right hand grip and determine the direction of current. We will determine the direction of current. So if north is this, north is to be here because the magnetic field, we know that north means the magnetic field is coming out, hence the current must flow this way, okay, in the coil. Okay, so we ignore this, we ignore this. Current is flowing this way, downwards, okay? Next, what do we see? Okay, now if we are to, if the current is increasing in the primary coil, how does the current increase in the primary coil? The moment we close the switch, current rises, right? Current rises from 0. Or we adjust the rheostat. You can see that the rheostat is in the circuit. So if we reduce the resistance in the rheostat, then the current will increase. Okay, so what happens when this change takes place, that the current is increasing? Now, we know that based on Faraday's law, current is induced in the secondary coil. Let's determine the direction of the current in the secondary coil based on Lenz's law. We know the current in the primary coil is this way. Now, based on Lenz's law, the current is induced to oppose the increase. The current induced in the secondary coil is to oppose this increase. So the current will be in the opposite direction. You must know that. So that a magnetic field in the opposite direction is created. Opposite direction to primary current. So the current in the secondary coil is opposite in direction to the primary coil. Something like this. Coil A is creating a magnetic field in the opposite direction. So what is important here that I want you all to know is the direction of the currents. If the magnetic current of the primary coil is downward, then the current of the secondary coil is opposite when there is an increase. But what if there is a decrease in current? Okay, let's say there is a decrease in current. How do we create a decrease in current? The switch must be open so that the current will drop. So we open the switch or we adjust the rheostat to increase the resistance. So if questions ask you, what do we do to decrease the current? Okay. Either we open or close the switch, we adjust the rheostat, or we use alternating current. Okay. Now, what is the direction of the secondary current? Okay, since this was the initial primary current, now the induced current will be in the same direction based on Lenz's law. Will be in the same direction because the current is decreasing. Hence, EMF is induced to oppose the decrease by trying to increase the magnetic field. Magnetic field is decreasing. So now coil A tries to maintain or top up the magnetic field. So the current will be in the same direction. So in objective questions, you can immediately put in the direction of current if you know this concept. Okay, let's try another question. Now we look at mutual induction in terms of, we look at the calculation part. We have looked at explanation part. We have looked at Lenz's law, how the current varies. Now we look at calculation. Okay, I told you all the equation earlier. The EMF induced in the secondary coil is the rate of change of magnetic flux running through it in the secondary coil itself, not primary. Because the secondary coil has a changing magnetic field running through it, so EMF is induced in the secondary coil. But the equation for flux in the secondary coil is the mutual induction times the current in the primary coil. This is the second equation relating to mutual induction. Because the flux through the secondary coil is proportional to the current running in the primary coil. Higher current, more flux goes through the secondary coil, right? So flux is proportional or equals, a constant, which is the mutual induction of both coils times the current in the primary. This mutual induction depends on the geometry of the coils, like how many turns, the area of the coil, the length of the coil, how long is the coil, L, and so on. Okay. Now we are going to insert equation 2 into 1 because equation 1 has flux there, but equation 2 is in terms of current. So when we insert 2 into 1, we get the voltage induced in the secondary coil is M, the rate of change of current in the primary coil. So MIP goes here. M is a constant, and we find that this is the equation we will use. So we have 3 equations we can use depending on the situation or the type of questions. Okay? Okay, so let's look at a question which has the values simplified like this. Okay, let's say we have a question where the current in the primary coil is changing or increasing from initial value 0 to final value. Now there you see DI P means the change of current in the primary coil. So this is the change of current in the primary coil. dt is the time taken for this change to occur. Mutual induction value is given. So what is the voltage induced in the secondary coil? So when we insert the values, let's try to insert the values. Okay, ES is equal to -10. The rate of change of current is final current minus initial. So final 1.5 minus initial over time. Okay, time is 1. So we will get here -15 and E's unit is volt. Okay, so we can clearly see that when the current increases, the EMF is such as to oppose this increase by a negative value there. The negative value is to show that the voltage induced is opposite to the primary voltage. The direction, if the direction of the primary voltage, if it's this way, the secondary voltage value direction is in the opposite direction. Okay, that's why it's a negative, and this is based on Lenz's law. Okay, now we continue with another example, which is just the opposite. When the current drops now, okay, with the same values given, then you're going to get a positive value. If earlier you got a negative, here you're going to get a positive, because final minus initial gives you negative. But don't forget the negative in the front of the equation, so gives you positive. So we can sum up that if the opposite negative E is opposite in direction to the supply voltage to oppose the decrease and oppose the increase, and positive is the same direction as supply voltage to oppose the decrease. That means the positive is to top up the magnetic field, and negative is to cancel off the excess magnetic field. Okay, now we are looking at derivation question. Earlier we looked at explaining the phenomenon, then we looked at calculation. Now let's try to derive the mutual induction, because deriving the mutual induction is a very popular STPM SEM 2 question. So you must be thorough at this part. Derive the mutual inductance, not induction. Induction is the process. Inductance is the physical quantity, M. So derive M. Of which system? Let's look at the system that they have given us. Here they show us two solenoids. You have two solenoids, one becoming the primary and one is the secondary. Okay, sometimes they can, the system can consist of a coil and a coil. And sometimes it can be a coil and a solenoid. It can be a coil with a solenoid. So you must be prepared for all possibilities. You have to practice the derivation. I will show you what happens when it varies. Okay. Okay, so how do we start? First step is to put in the equation we looked at earlier, right? What's the equation we looked at earlier? Let's go back and see which equation are we going to use to determine the mutual induction. Inductance is either 1, 2, or this one. It's best we use this. Flux is Mi. Because we don't have the EMF induced. Let's see the question. It depends on the question. Let's look back at the question. Oh, the question didn't mention anything, but the question didn't give us the EMF induced. So we start from basic. What is the flux? the flux and the mutual inductance, the equation relating. So the flux through the secondary is mutual inductance, the current in the primary. Now we will replace flux as, remember the equation for flux, NBA cos theta. Okay, but most cases cos theta is 1. So in this case also, if you analyze carefully, cos theta is 1. So flux is NBA of the secondary. But the magnetic field is generated by the primary coil. Okay, so we have to substitute B as from the primary. Okay, now what do we do? We have to insert the magnetic field of the primary coil. But here the device is a solenoid. So magnetic field of a solenoid. What is the magnetic field of a solenoid? The magnetic field of the primary is a solenoid. So magnetic field, if you recall back, magnetic field of a solenoid is mu naught Ni, or mu naught capital Ni over the length of the coil. So we're going to insert that here. Okay. Now we can see that there is current on both sides, right? We want to simplify. We've already inserted and there's nothing more to insert except now to simplify. We started with the main equation, inserted the flux equation, inserted the magnetic field equation. Now it's a matter of simplifying. So we cancel off the current. Of course, here they're just showing the equation. We have substituted N as NP over L. Okay, now cancel off the current. And we have already derived the magnetic field, mutual inductance. Okay, which we rewrite it in the right way. So it's very easy, right? You have to just remember the equation for mutual inductance. For self-inductance, the magnetic flux is equal to L, which is self-inductance, times the current. And then again, flux is NBA, and B we will insert and cancel off the current to get L. So go back and revise that. Revise that later. Okay, so now what happens, as I told you, if the system is not a solenoid, but a coil solenoid. Let's say the coil is the primary, okay, because this is, you have to insert the primary. Now, if they said that the coil is the primary, so what we have here, let's say we have a solenoid, okay. Okay, and then in the center, let me change the ink first. Okay, so here we wrap around a coil. We wrap around a coil and we let current flow through it. So now the coil becomes the primary. And the solenoid is the secondary. So for the solenoid, we will place maybe a voltmeter to determine the EMF induced. So we can draw a voltmeter or a galvanometer to check the current direction. Okay. So now, in the part B primary, we will replace with the magnetic field of a coil, which is mu naught Ni over 2R. Then the rest is the same. Everything else is just follows through. Okay. And we will be able to derive the mutual inductance of the coil solenoid system. What if it's a coil? So you have to derive for coil. But coil is the same as coil solenoid, because the only difference is the magnetic field of the primary. If it's a coil also, it's still the magnetic field of the primary is a coil. and the rest is the general equation. Okay, so please practice on that. Okay, now we move on to a question similar to STPM question. This one is on rotating coils. It's a coil, but it's rotating. So what are we going to calculate? We want to calculate, for example, the change in flux. And from the change in flux, maybe they want us to calculate the EMF induced. It's a bit more challenging because it involves angle. Okay, so we have a coil like this, and the coil is said to rotate by 180 degrees. So now the front surface is now on the other side. So let's say you have a book. The book has a front cover and back cover, right? So now the front cover of the book, which was actually this stripes, the shaded area, is now rotated by 180 degrees. So you can see it here now. Okay. So what is the question? Normally they will ask you to calculate flux, the change in flux and the EMF. If they ask you to calculate the EMF, then you have to calculate the change in flux. Okay, so we recall back the equation for flux. Equation for flux is NBA cos theta. And theta is the angle between B and the normal of the area. Where is B in the first diagram? B is this lines, the magnetic field lines. Where is the normal of the area? Let's say we have an area like this. Now the normal of the area is perpendicular to the area. So in the diagram, the first diagram, we find that the normal of the area is parallel to the magnetic field. So the angle will be 0. Theta in this case will be 0, and hence cos theta is, cos of 0 is 1. Okay, let's say the values are given. We have a coil that is has 5 turns. The magnetic field strength here is 10 Tesla, and the area of the coil as shown in the first diagram is 1 meter square. Okay, calculate the initial flux for the first diagram and calculate the final flux in the second diagram. And the change was said to happen in a time of 0.2 seconds. What is the EMF induced? Okay, so initial flux, when we insert the equation NBA cos theta, N is 5, B is 10, area 1, and cos theta is 1. So we will get 50 Weber. Okay. For the second part, okay, in the second diagram here, the angle is also the same because the normal of the area is still parallel to B. So cos theta is still 1. So when we put in NBA cos theta, we will get N as 5. It's still the same number of turns, the same magnetic field strength, which is 10. The area is still 1 meter square, and cos theta is 1. But don't forget you have to place a negative. Now here we must place a negative sign. Negative sign is placed when the flux is exiting the area. So flux, although it is a scalar quantity, but it has positive and negative sign, and you need to know when the positive and when to use the negative. So when the magnetic field enters an area, the flux is placed as positive. And when a change occurs where the flux now leaves this area, this front face lah, then the flux is going to be placed with the negative sign. That you must know. Okay. Normally we don't come across questions that test us on this, but it's in our syllabus. So it is negative 50 Weber. Okay. So therefore, the EMF induced is negative the rate of change in flux. So therefore, we will place negative final value, which is negative 50, minus the initial value 50 over the time taken, which is 0.2. So this gives us a positive value of 100 divided by 2, which is 0.2. This is 100. 100. So it's 2,000. Yes. No, 500. Right? 100 divided 0.2 is 500 volt. Okay, so this is the answer. Many students were unable to get the correct answer because they did not place the negative sign when the coil turned by 180 degrees. Okay, let me clear. Let's discuss if the coil turned by 360 degrees, what would have happened? So if the rotation was 360 degrees, the phase would come back to its initial, right? So now this phase returns back, the same phase. And here the magnetic field will again enter. If it was rotated by 180 as shown in this diagram, the front phase is now here and the magnetic field is exiting it. That is why we had to put a negative. But if it's rotated by 360 degrees, the magnetic field is back to entering it. So earlier you got a positive of 50 Weber. Here again you will get 50 because it's positive NBA, no change, positive NBA. Flux is NBA. Now the sign remains positive. So E would be final minus initial, negative final minus initial, which will give us 0. 50 minus 50 is 0, negative 0. So which is 0. So the EMF is 0 when the coil returns back to the maximum flux. If the coil turned by 60 degrees, how? We have discussed coil turning by 180, which is easy. Coil turning by 360. What if coil turns by 60 degrees? So now we need to apply the angle. So the coil turned by 60 means the magnetic, the normal would have turned by 60 degrees also. So here you see, let's discuss. This is the normal, okay? Normal of the area. Now when the coil turned by 60 degrees, the normal has also turned by 60 degrees from its initial. So the angle between the magnetic field B and the normal of the area is 60 degrees. So you turn by 60, the normal also turns by 60. So our final expression would be NBA cos theta, and now cos theta is replaced as 60 degrees. So 5 for N, B is 10, area 1, cos 60 degrees. So we would get a value, right? That is just minus off with the earlier initial flux over time, and you get your ES. Okay, so we have discussed different possibilities. Okay, now we move on. Understanding direct current. What are we going to understand here? Direct circuits. Like for example, sometimes understanding the circuit is a challenge, right? The circuit may look complex. So we try to simplify, discuss to simplify our understanding and discuss how to simplify the circuit. Okay. Okay, so let's look at the case where current flows from A to B. One thing you have to understand is when current flows from A to B, it means that the voltage at A is greater than the voltage at B. That is why the current is flowing from A to B. Yeah? If the reverse takes place, current flows from B to A, then VB should be greater than VA by the value IR. That means V is greater than A by Ohm's law, V is IR. So if I know the current and I know the resistor, let's say I is 1 ampere and R is 3 kilo ohm. So V is IR, which is 3 kilovolt. Okay. When I times 1 times 3 kilo, I get 3 kilovolt. It means that VBA is 3 kilovolt. B higher than A by 3 kilo. Okay, now what if you have a battery with the positive facing A and the negative facing B? We know that positive is a higher voltage and negative is a lower voltage. So we can say that VA is greater than VB because the battery's positive terminal is facing A. Now, if we were asked to calculate or determine determine the voltage at point A, it would be 9 volt because the positive is at A. Okay, and we take A as 9. If A is 9, then B should be 0 because the voltage supply, the battery's voltage is 9 volt. So if A is 9, B is 0. Hence, the voltage AB is VA. This is the equation. If you have a question which asks you to calculate VAB or VPQ or V whatever, it is the first letter minus the second letter. And since VA is 9 and VB is 0, 9 minus 0 gives us 9 volt. What about VBA? So we still write the equation. VBA is VB now minus VA. What is VB from above here? VB is 0. VA is 9. So 0 minus 9 is negative 9. What does this indicate? It indicates that B is lower than A by 9. Because it's negative. Negative indicates a lower value. Positive indicates a higher value. So like VAB is positive 9. VBA is negative 9. Okay. Okay, let's try a direct circuit question like this. Okay, let's say they want us to calculate the voltage at points 1, 2, 3, 4. What is the voltage between 1 at point 1, 2, 3, 4? Or maybe what is the voltage across 2, 4 or 1, 3 or 2, 3 like that. This is very common in your in your STPM SEM 2 question paper. It's a very popular question. Okay, so first thing is to find the circuit current. The current must be known. So we simplify the resistors. They are in series. Net resistance you can see is 3 plus 10 plus 5, which is in series. So we add them up, it's 18. And the voltage is 9. So using Ohm's law, we are able to calculate the current 0.5. And we must know the direction of current is easy because the voltage, the battery, it's only one battery, yeah, with the positive facing clockwise. So the current is clockwise. Okay, now we are asked to calculate the voltage 1. Voltage, not voltage, the voltage at point 1. Not the potential difference. This is potential difference between 2 points, PD. But at a single point is the voltage. What is the voltage at a certain point? Okay, just like what we did earlier, because the battery's positive is facing 1, there's no resistance between 1 and 4, so we can immediately write V1 as 9 volt, and V4 as 0 volt, like what we discussed earlier. Now, what about V2? Since V1 is 9 volt, what is the voltage at V2? Let's look at the current flowing across the resistor. The current flowing across the resistor causes the voltage to drop from 1 to 2. Because as I told you all earlier, current, wherever current is flowing, that point is higher voltage. And the point is flowing to, the voltage will be lower. So the voltage is dropping. As the current flows from point A to B, the voltage drops from A to B. So let's calculate the voltage drop, which is Ohm's law. V is IR. We find the voltage, the potential difference. So we can say that at point 1, 2, the voltage between 1, 2 is IR, and we calculated I to be 0.5 and R is 3 kilo. 3 kilo. So we get 1.5 kilovolt. Oh, the resistors don't match, because you can't have voltage dropping to kilo. So I think we can remove the kilo. Doesn't make sense, because the current is 9 volt. Oh yeah, sorry. 18 here is kilo. Remember, let me just because the resistance here was 18 kilo. So the current is kilo ampere, 9 over 18 kilo. Oh, 9 over 18 kilo will be 0.5 milliampere. Sorry, Okay, let me just erase first, or drop off this part. Erase it. Okay. Okay, so resistance is 3 plus 10 plus 5 is 18 kilo ohm. So 9 divided 18 kilo is 0.5 milliampere. So now when we put milli with kilo, now we get a nice value, 1.5 volt. Okay, so the voltage drop between 1 and 2 is 1.5 volt. So we can find 2, the voltage 2. We know V1 is 9 volt. V2 is how much 1 has dropped by. It has dropped by the voltage difference of 1.5. It was initially 9 volt. So when we minus 1.5, we get 7.5 volt. So at where the current flows, the voltage is dropping by IR. So now how about 3? The current is again flowing through the resistor, causing the voltage to drop again. So V2 must be less than V3 by IR. So what is V23? It is equal to IR. So I is our 0.5 milli and R was 10 kilo. So we get 5 volts. So voltage at 2 dropped by 5 volt. Okay, so it was voltage 2 was 7.5. It dropped by 5 volt to become 2.5. Because 7.5 minus the voltage difference, the voltage drop is 2.5. Okay, now the last part. But last part we already got V4, isn't it? V4 is 0. If we want to prove it, I'm not sure whether the values will be correct. I just generally took it. Okay, so let's say the current was 0.5 milli and the resistance is 5. Yeah, we get it correct. So V34, using Ohm's law, which is IR, the current is 0.5 milli and the resistance is 5 kilo. We get 2.5 volt. So the drop is 2.5. So let's check. The voltage 3 was 2.5. It dropped by 2.5. 2.5 minus the drop 2.5 gives us 0. So correct. Okay, so this is how we solve a question which asks us to calculate voltage at a certain point. Okay. Now let's try a slightly more challenging question. No, this is not that challenging. We try. This one. Okay, let's try this question. It looks quite complicated. They ask us to calculate the voltage at points P, Q, and R. So how do we solve this? We know the voltage at S is 0. Immediately we know voltage at S is 0. Why? Because it's connected to the ground. To calculate the voltage drop, we need current. So we have to use Kirchhoff's second law, or yes, Kirchhoff's second law to determine the current. Okay, so we can say that the sum of EMF is the sum of IR. Since it's a series circuit, we can place the current in a particular direction and it's going to be the same current all the way. Okay. Okay, so what is the sum of EMF if we are going to look at the loop which is in the anti-clockwise direction? We find that we will add, since we are going anti-clockwise, the voltage of 15 is positive and the voltage of 5 is also positive in the positive direction, because from low to high, the voltage as we go in the anti-clock is from negative to positive, so we're going to add it up. Okay, the sum of current, since the current is constant, we will place I with the sum of all the resistors, which is 3 plus 2. Okay, and the current direction is the same as the loop direction, so it's positive. So 20 is 5I and I is 4 ampere. Okay. Now the next step is to find the drop in voltage for point P, from S to P. Is there any drop in voltage? Yes, there's just a battery between S, let's draw S to P. S to P, there's no resistor, but there is a battery. The voltage at S is 0, but the voltage at P is lower by the battery voltage. Why? Because the negative is facing P, lower voltage, and the positive is higher, facing S. So the drop is 5 volt. So we can state or clearly deduce that the voltage of P is lower than S by 5, so voltage P is negative 5. Okay? Now we go to point Q. Okay, so we draw P and Q. We know voltage at P is negative 5. Now we want to find the voltage at Q. There is a resistor between P and Q, no battery. But the current is flowing from Q to P. Current makes Q higher than P by IR, by the voltage IR, V. Because the current is flowing from Q to P. VQ must be greater than VP, right? By how much? By the current times the resistance. So let's calculate that value. The current times the resistance. VQP is IR. I is, we calculated here, there you see here 4, and the resistance is 2, so it's 8. Now, VQ is greater than VP by 8. If VP is already negative 5, what is VQ? We know that Q is greater than P by 8. So, if VP is already negative 5, I now need to go up 8 places. It needs to be higher by 8. So, when I add 8, negative 5 plus 8, I will get positive 3. So, therefore, VQ is positive 3 volts. Okay, so we can say VQ is positive 3. So far we have got VS as 0, VP as negative 5, VQ as positive 3. And we follow along. Okay, let me just finish up the last part. Okay, so we got P0 here, negative 3 volt and positive 5. Now, the current we know was, I forgot what was the current, 4 ampere. Okay. Now, which is higher? Let's draw QR. We need to find R. So we draw from Q to R. Current is flowing from R to Q. Remember, we deduced the current flowing from R to Q. This makes R greater than Q by the value of Ohm's law, which is V is IR. So, but Q is already positive 5. So R needs to be higher because the current, as I told you, how do we know R is greater than Q? Look at the current direction. If current is flowing from R to Q, current, it makes R greater than Q by the voltage difference. So I is 4, R is 3, so it's 12 volt. So R is now 12 volt higher than 5. So 12 plus 5 is 17 volt. Something is wrong with that. 20 is 5, so 4, correct. Correct, 3, 12. Yeah. 12 plus 5, 17. Okay. Understand? So this is how we are able to calculate voltage at P, Q, and R. Okay, so I think we have already finished the time. It's already 10. So maybe we can look at any questions that you would like to ask. And I leave it back to the host to handle from here. Okay. So I shall stop sharing. Okay. Is there any questions anyone would like to ask? No. Okay, thank you, dear. No questions, huh? Okay, so in that case, then is any of the YPC admin here to handle or to take over? Yes.
Terima kasih diucapkan kepada Cikgu Cahaya Selvi di atas perkongsian yang cukup jelas pada malam ini. Tidak lupa juga ribuan terima kasih diucapkan kepada pelajar-pelajar dan guru-guru STPM 2024 yang mengikuti program kita pada malam ini. Diminta pelajar-pelajar yang join untuk mengisi kehadiran boleh klik pada link yang disediakan atau scan pada QR code yang dipaparkan. Untuk makluman semua, seminar yang seterusnya adalah mata pelajaran biologi yang akan berlangsung pada 12 Ogos bermula jam 8 hingga 10 malam di platform Zoom dan juga YouTube. Jangan lupa untuk klik link pendaftaran untuk mendaftar. Seterusnya dijemput untuk follow media sosial kami di laman Instagram, Facebook, TikTok dan subscribe channel YouTube YPC International College untuk mengikuti seminar yang seterusnya. Terima kasih dan selamat malam semua. Jumpa lagi pada program minggu hadapan. Terima kasih, Cik.
Thank you. Terima kasih. Thank you.